Hello, my name is Emmanuel De Leon, and I will be presenting an overview and review of structural health monitoring for aerospace structures and components. As an outline to this presentation, I will provide background as to why there is a need for structural health monitoring of aerospace structures as well as its challenges, discuss the state-of-the-art developments in sensor technology and its applications specifically for aerospace structures, introduce airworthiness requirements for SHM systems, and conclude with final remarks. Currently in the aerospace industry, the typical maintenance practice relies on the use of conservative, time-based, or usage-based scheduled overhauls, which are overly time-consuming, labor-intensive, and very expensive. In addition, maintenance service frequency and cost both increase while the component's performance and availability decrease. Furthermore, traditional non-destructive methods tend to often involve extensive disassembly of structural components to access critical areas of inspection. Current practices are a result of the difficulty in predicting the in-service conditions and failure modes accurately, as they are typically complex in nature. Applications of structural health monitoring for aerospace structures have many benefits that can increase safety and reliability. Namely, structural health monitoring can provide early indications of physical damage, which can be used to define strategies to mitigate structural damage before failure occurs. This one advantage has been showing great promise in the aerospace industry, as it will help reduce maintenance costs, save structural weight, and reduce operating costs. Differences in both traditional and SHM technologies can be seen in Table 1. While both methods tend to provide information on component health and condition, SHM has the ability to provide real-time states of parts, unlike the NDT counterpart. While SHM shows great promises within lab environments, its transition to the field is slow. Major civil aircraft OEMs, such as Airbus, Boeing, and Comac, have been evaluating the technology but have not prevailed to incorporate it within their civil aircrafts yet. There are multiple reasons why incorporations have been slow. First, years of experience and expertise are required to know where and how to install sensors for optimal damage detection for all new applications. Second, many SHM systems are not built with self-diagnostic capabilities, which can be difficult when trying to distinguish between actual structural damage and sensor damage. As aircrafts tend to operate in extreme environmental conditions, most SHM systems are very sensitive to environmental changes and are unable to effectively compensate to allow for practical use. As for probability of detection and damage quantification, most SHM systems cannot easily provide quantifiable specifications for new applications and configurations, which hinder in providing quantitative damage sizes with associated uncertainties. In order to be installed on aircraft applications, the SHM system must comply to airworthiness standards in addition to its intended functions. Airworthiness compliance requirements are discussed later in this presentation. While the listed challenges are presented, these elements are also necessary for a complete and robust SHM system. State-of-the-art developments in SHM systems have been considered greatly in the monitoring of aerospace structures from metals to composites. In this presentation, 3 sensor systems are individually explored with their experimental applicability to monitor such structures. First, fibre Bragg grading sensors are commonly used as precise and accurate strain sensors. Centered around the Bragg wavelength and its shifts to temperature and strain variations, measuring this shift allows to determine the mechanical strain at the location of the FBG. Recent developments have been made to embed optical fibers in its host structure, which is detailed in this presentation. Next, piezoelectric transducers are able to actuate signals or act as sensors due to the piezoelectric effect, as it is able to generate an electrical response from applied mechanical strains. These sensors are typically mounted on or embedded into its host. An application in rotating turbomachine structures are discussed further in this presentation. Finally, Acousto-Ultrasonics is a guided plate wave-based inspection mode that performs diagnostic coverage at a wide area with relatively low sensor density and can be applied to metallic and composite structures. This method depends on piezoelectric wafer active sensor elements to generate the interrogating wave field. In addition, it can also employ either PWAS elements or optical FBG to sense the scattering field. A novel AU system is also discussed in this presentation. First, we will discuss FBG sensors. As aforementioned, the optical fibers are typically embedded on host structures. However, there have been few solutions in ensuring the sensors are protected and bonded to composite structures. Specifically to the intense in-flight conditions of aerospace structures, no adhesive material and bonding procedure had been tested. An experimental study was completed in Europe that addressed this shortcoming by proposing a solution using draw tower fiber brag gratings coated with glass fiber reinforced polymer and high-density polyethylene called strain measurement wire. Coupons were tested using aerospace standards, where the testing conditions are shown in Table 2. For the experiment performed, if any local damage was done to the sensor or the coatings due to any applied load, this resulted in local non-uniform strain field around the DTG and would be able to observe a distortion of the reflection spectrum of the Bragg peak. To quantify these expected observations, the cross-correlation between the Bragg peak before and after the tests were compared. It was found that there were no noticeable changes in the peaks, which concluded that the proposed mounting method was successful. There was no damage induced in the DTG sensors nor the SMW coating under any flight condition. While SHM of aircraft-specific components are common, it should also be considered for rotary aerospace structures because their failures can ultimately lead to catastrophic mishaps. An experiment was performed to monitor gas turbine engine blades when operating at semi-field working conditions. For this experiment, 6 superalloy Inconel 718 turbine blades were monitored via the electromechanical impedance response of PZT sensors. A notch was introduced on the leading edge of the blade, and the condition of the blade was compared to that of a baseline blade. Figures 2 and 4 show the schematic setup and the prototype of the experiment, respectively. To measure differences between the blades, shifts in the frequency of the EMI signature were detected. As the damage grows, new peaks in the impedance were measured as it grows from its minimal detectable size. While frequency shifts are justifiably detectable in the blade stationary mode, it is believed that mechanical resonance has a role in the reduction of the detectable damage size. First, centrifugal loading as the blade rotates has the effect of stiffening the blade, which increases the natural frequency when compared to the stationary mode. Second, random impedance peak amplitude changes can be experienced by aerodynamic load fluctuations, including changes in the dynamic drag pressure and random impacts of high-velocity air particles into the transducer. Despite these influences, the proposed technique for SHM of rotary parts can successfully detect formation of early damages prior to failure. It can be seen in Figure 13 that there are clear shifts in the frequency of existing peaks of the baseline, changes and formation of new peak amplitudes, and an increase in the EMI signature, which completes the damage detection expected. The novel AU interrogation system called the Acousto-Ultrasonic Structural Health Monitoring Array Module Plus, or AU SAM Plus, is a SHM system that provides autonomous control of 4 PWAS elements capable of sending and receiving signal information. The AU SAM Plus is seen in Figure 1. The system is able to perform self-diagnostics in addition to structural health monitoring through electromechanical impedance measurements. The system has a high bandwidth range for the excitation of higher order AU modes. With the rise and interest of FBG sensors, they can be interfaced within the module for additional signal collection. As it will be seen in the experimental results in the next two slides, damage detection using FBG sensors is well supplemented to the PWAS information. The module is also capable of monitoring voltage and current waveforms, which proves useful to the signal acquisition. More detailed and analytical information on how this is performed is detailed in reference 3 of this presentation. Finally, the module is capable of scaling. Additional systems can be easily added to the whole architecture for monitoring. The AU-SAM Plus system capabilities were demonstrated through damage detection of metal and composite aerospace structures. First, metal detection was done for both an aluminum panel and aircraft wing skin specimen. For both cases, a notch structural damage was placed in figures 25 and 32 as shown. For demonstrating the EM capability of self-diagnostics, Figure 25B shows a PWAS element exposed to beeswax and acetone to simulate sensor damage. For the aluminum panel, results show good stability for measurements at all frequencies for the PWAS element and some for the FBG sensors. At a low test frequency of 150 kHz, Figure 26A shows a decline in magnitude for the S0 and A0 wave packets, while the A0 mode was barely excited in the 550 kHz case in Figure 26B. For the aircraft skin specimen, Figure 33 shows that the chosen interrogation regime offers a good basis for inspecting the particular structure specific to the wave packet caused by the notch. The SHM of a composite aerospace specimen was also demonstrated with the AU-SAM Plus, where the damage was made by a dropped impact to the specimen as seen in Figure 35. The results shown in Figure 36 is similar to that seen with the aircraft skin specimen, where strong attenuation was observed for all frequencies. However, the impact damage applied in this case was beyond the threshold of barely visible impact damage. Therefore, work is needed to further assess the performance of the AU-SAM Plus. Although SHM systems can be well integrated into aircraft systems, as shown by the three examples in the previous slides, the important consideration of airworthiness must be met so the systems can be considered practical for application. Since the SHM system is electrical, it must meet its respective regulations such as power supply, anti-static protection, fireproofing, radiation protection, and many more. As the system is to be integrated within the structure of the aircraft, it also shall meet electrical wiring interconnection system regulations. These include design and installation of wires, cables, connectors that must meet requirements such as electrical grounding, physical isolation, and material flame retardant. Finally, as the system is installed on the aircraft, consideration for the respective installation regulations for airworthiness, which includes weight, load distribution, material compatibility, durability, as well as accessibility of the overall system must all be met. This is not to mention that the SHM system must be easy to use and set up with a simple GUI and be able to detect and assess structural damage with light to minimum damage size to be detected and a POD. In conclusion, SHM of aerospace structures and components show great promise. It was provided that SHM can be applied and save in maintenance costs, as well as provide real-time diagnostics without the removal of components to reach critical areas of the structure. Also, experimental cases presented show viability in applications of SHM systems into the structures. As presented, there are various methods in capturing shifts in the suspect component based off the baseline structure. In addition, SHM is possible in any flight conditions while allowing for sensors to remain intact to the host structure. While it is possible to apply SHM systems in aerospace applications, airworthiness requirements must be met for the practicality of monitoring as to ensure it will meet and support aircraft's required mission. That concludes my presentation. Here are my resources, and thank you for listening.